Everyone, today I am going to show you how to design SPR sensor, that is Surface Plasmon Resonance based sensor in ANSYS Lumerical FDTD simulation. At first we have to open ANSYS software. Then we will go from this new option, then FDTD, and we will do FDTD here. So now this is the FDTD window, and this is the interface of Lumerical software. Here we can design a SPR sensor that many researchers do work on SPR sensor design, like that can be used for glucose detection, biomolecule detection, cancer detection, and a lot of uses. I will not discuss a detail about theory and other stuffs. Just I will focus here the main design sector. So let's start. Here in top you can say file, edit, view, settings, simulation, and many other things. In SPR sensor, normally we use the nanometer range, so I prefer from here the setting that is length unit in nanometer. I will choose this nanometer. Then I am going to show you in the second ribbon here materials, structures, attributes, components, groups, simulation analysis group, and a lot of things, source, monitors, port. At first this is the material section. In this material section you can design material, or you can use the default material from here, like this aluminum material, and the simulation actually based on the refractive index. So we need to use the different refractive index value of a different wavelength, that is here. But if we want to design a different different sensor using new material, like except gold, and if we want to use these, like I will not use this default material. I will create another material that will be different refractive index. That can be possible by using this add option. In add option there is a lot of material, like NK material, analytic, dielectric, debye, and a lot of things. And normally we will use here the sample 3D data, like here sample 3D data is here. If we click at sample 3D data, then new material, like I will use say silver material, that is silver, and I will give another name like silver test. Then go to silver material that already created here silver test, and we can change the color of this material from this section, because when we will use different material like silver, like silicon dioxide, like barium titanate, and also another material, that we need to use different color for our to design or to understand the different color of different material. Then just focus here, like I can set it this color or this color, green or yellow, as my wish. Okay, then from here actually the SPR experiments have done at helium neon laser light, and it has a wavelength of 633 nanometer. So we will set that 633 nanometer, but look at here, the wavelength is in meter, E minus 9, that is 633 nanometer, and the refractive index value can be found the metal from the Drude-Lorentz model. That's something like, say for example, I will use 0.05 and 2.3. That, for example, I use that value, but we need to confirm this from different experimental work or other theoretical calculation. Then if we add OK, then a new material has been added to our material library. Then here is a structure. If we use 2D rectangle or a normal rectangle, then we have to declare this rectangle, or if we want to design another type of material, triangle or circle or sphere, then we can design it very easily. So I need to use here a rectangle material, so I will set it as rectangle. So here you can see this is rectangle, and for SPR at first we use glass material. That here, like, I will use a glass material, and this glass material is normally called as prism. Then here this is prism, and this is rectangle. And if we grow it, at first you need to set the geometry and material. When I will right click on prism, then there will be a window like rectangle, and this is our material section. Like if we use silver test, that has been created already, but if we can use silver material like silver Palik model 0 to 2 micrometer. It is possible. Then we can use geometry. Like I prefer the geometry setting at x-axis, that I will grow the material over x-axis, and I will keep the y and z axis fixed. So this is arbitrary, but actually the thickness of each layer has a profound impact on design parameter, but prism has less impact. That has been claimed in different research work. Like prism thickness is not very important in this design, so we can choose a different type. Like if I choose this from 5000 to that can be minus 50, no problem. Then I will set it to minus 1000 nanometer to 1000 nanometer, and this can be minus 500 to 500 nanometer. Look, if I apply this, then my silver material my prism material has been selected. Sorry, here prism should be not prism cannot be silver. Silver is metal material, but we need to select prism material for material database. Like I can use silicon dioxide, because silicon dioxide is a glass that is here. I will use silicon dioxide as a glass. Okay, just I have chosen silicon dioxide. Then I can duplicate this prism, or I can add another 2D another rectangular structure. But here there are a lot of options. See here, the second item, this duplicate item. When I will click here and then click prism, then it will create a duplicate layer. Like duplicate from here, I can use, I can edit the object like that will be silver material, and the material will be silver, just silver Palik model, and geometry can be set as it that the previous layer is the last point was that I am going to the previous prism. Like here, look, minus 5000 to minus 550. So okay, then I am going it to x-axis. So the y and z will be fixed value for all material. Then when I will edit silver material, just the prism material was ended at minus 50 nanometer. So I need to correct this. I will set silver material 0. That is from different study that the 50 nanometer silver can perform better in different SPR sensors. So we choose that here minus 50 to 0 nanometer, and here minus 1000 to 100, and minus 50 to plus 50. That will be almost same, and the material will be silver Palik. Okay, done. Now we are almost there. Okay, that I have chosen two different material like prism. See here, the prism material, the direction of x-axis in prism material is 2y, that is 5000 nanometer, but when I will use the silver, that is very narrow and only 50 nanometer. Here you can see that the thickness of silver material is 50 nanometer. Okay, so let's go. We can then prism and silver is almost done. So we need to use light source. At first I told the light source will be helium neon laser light and the 633 nanometer, but in practical simulation segment we need to use source like plane wave, or there are different type of light source, but here we will use the plane wave, that is helium neon laser light. And before going to light source, we need to define the FDTD region, like FDTD, and also there are another factor, materials, like when we will use say biomolecule, that may be urine glucose, that may be alcohol, that may be gas or formalin or different type of algae. So then we will select materials from here, then add, that is analytic material will be used here for to define different analyte. Like here, when I will click the analytic material, then look, I will give the name of this layer analyte, and I will set the name color of analyte material, like here where is analyte, here analyte material, like I will set the color of analyte material just this color. Okay, then I say the refractive index of water is 1.33, and from here I will use that, because we need to define two we need to calculate the sensitivity or performance parameters from two different refractive index value. So at first we will define it as the water value, that is 1.33. So okay, I don't need to change other parameters here. I have said the real value is 1.33 here, just 1.33, and I can duplicate this silver layer again, but I will give the another name, that will be analyte. and from here edit object, go to material, choose analyte, this is here analyte, and then go to geometry, and from geometry that the silver was -50 to 0, so analyte can be 300 or 400 nanometer. Here I will use 0 to say 300 nanometer. Then and other dimension will be same, y and z, just x-axis, because I am going this along x-axis. Now apply, okay, and here you can see it in a very see it very easily, like analyte is this green color, and now you can see the prism silver and our analyte. Now we need to do the at earlier I explained we are going to design a SPR sensor by using Lumerical FDTD, and now this is the term FDTD, finite difference time domain method, and I will import these FDTD region, and that will be add FDTD. But FDTD will actually calculate or solve the Maxwell's equation, so I need to as my in every small grid, look here, there is a symmetry. So if I can define it in a small region, then I can say that our design will show the symmetry. So so there is no need to consume much more memory, because FDTD calculation will take a lot of memory. Also the computational power also consume the computational power, so we need to use this in a very shorter position across the design. So now I will design this FDTD. I will set the geometry of FDTD here, edit object, geometry, and I will set it here 2D FDTD. You can check the ANSYS Lumerical's website where you can set the 3D FDTD, 2D FDTD, and there are a lot of differences of 2D and 3D FDTD and other FDTD. Like 2D FDTD is efficient, and in this design we use this 2D FDTD, and from here the other parameter will be same. There is background material, the refractive index 1, that means the actual to give the practical vibe in the simulation, like the AR has the refractive index of 1, so we use the FDTD refractive background refractive index material is 1, that is we are conducting it in AR, that is here the final geometry. Now I am going to set this geometry, and the FDTD geometry can be -500 to 1000, that's, and other value can 1.25 to 1.25, and that is 2D FDTD z-axis will be disabled here. Now the FDTD region is set, and other from here the other condition like mesh type, auto non-uniform or minimum mesh step size, I will set another mesh after this, and this is the boundary condition, and you can say the boundary condition here, that is along the x-axis we use PML, and for y here we use the block. I am not going to make this video long, because then it will be very long if I discuss the each and every point why I use this. Just I am showing you how can we design an SPR sensor using this software. So then I'm going to design this, and these the layers. Here I can use 12 or 16, or it can vary, and the other value will be same. And here if I remove this, then I can say auto scale PML parameters, or I can keep this, or no problem. If I keep this keep like this, then it's just coordinate PML, and almost this same. And for advanced option, the default option is okay. Now I am going to accept changes. Then FDTD has been set, and you can see the FDTD region is here. This is the FDTD. Just this long yellow portion is FDTD here. Now I am going to set the mesh size. Mesh size will take the area of silver to analyte regions area, that the simulation will be divided into a small mesh, and then it will calculate it. And look, this is the mesh, and I am going to set this mesh by setting its geometry. Like here, I will set the geometry here, like mesh as it was -50, and we can use the mesh here to -50 to 0 to 300. That's why we used -50 to 300, and the mesh x-axis will be 350. And here we can set it like just -35 nanometer to 35 nanometer, and here just we can set z-axis like -5 that will be z span, that is 5e5. Apply, and also apply, then general. And here from general, that I will override the x-axis mesh. And here is another crucial parameter, the dx, that is this. If I use this long value like 2 or 5 or 10 nanometer, then it will use the less memory, it will use the less computational power. But if we set the mesh nanometer very short value, then like if I set this 0.01 nanometer, then it will set each mesh 0.01. it will calculate after 0.01, and it will take a lot of time, but it will enhance the accuracy. But we need to trade off the whole thing. Like here I can use if I use 2D material like graphene, then graphene has the atomic layer thickness is 0.34 nanometer, so we need to set the mesh less than 0.34 nanometer. Here I can set that is 0.2 nanometer, that is no problem, 0.2 nanometer. Okay, and see from here the mesh size is here, and that is from the starting of silver to end of the analyte. And if I disable mesh, you can see that here if I disable mesh, you cannot see the mesh from here, but if I can enable, just look, this is the mesh, and the entire simulation will be divided after 0.2 0.2 0.2, and it will calculate each vector after 0.2 nanometer, that is a mesh setting. Then look, I have already designed the structure, the FDTD region, actually how to will compute the Maxwell equation, then the mesh setting. Now we need to use the source, like light source, because here we will use the light source as the main parameter. Like light will be totally internally reflected here, and then a evanescent field will create here, and that will actually propagate through this place, and we can calculate electric field, magnetic field from evanescent field, and that evanescent field actually helps us to calculate the sensitivity and to design the sensor. So I am going to set the light source, and you can find the light source from here, that is source. We will use the plane wave source, that is plane wave source, plane wave source. Just I can set the name source 1, no problem. And here the direction axis, as I have grown the material along x-axis, so I will set the injection axis along x-axis, and that will be forward, and other thing need to be same. Then I will set the actual geometry of this source here. From here I can set it as 200, no problem, because just we need to set the source behind the prism and metal interface, and prism and metal interface was there at -50. You can go to the previous section of this video, and then you can see the actual point that was -50. So I use that is -200, and finally I just set this as before, -2.5 nanometer to 2.5, that is here. Then this can be as before, -1000 to 1000 nanometer. That's okay. That's our simple source. Here we can use different wavelength that we will use here, like 633 nanometer. Just I have said that 633 nanometer. Then enter. See, this is the light source. Here x-axis forward, just you can set also you can set the angle from here, because we know that for total internal reflection we need to set the source more than critical angle, but we don't know what will be the critical angle here. Just we can set it at 40 degree, no problem. Just if we can set it 40 degree, then you can see from here that is light is already inclined as 40 degree. Then we have done everything. Just we need to monitor what happened here. If we run simulation, that we need to collect the data. So for data we will set monitors from here, Like first we will set the time monitor, that is time monitor, that will keep the value, and from here we will set the uh, geometry of time monitor, that is just normally here -4 to 5, and finally that is, and here the actually data to record output electric field or magnetic field is along x-axis, y-axis and z-axis, no issue. Okay, I will set it as -4 to 5, apply. Okay, that will be time monitor. Now after time monitor, I need to use the reflection monitor and also electric field monitor. From the reflection monitor we will calculate the actual sensitivity, FWHM and other things, and from field monitor we will calculate the penetration depth, how the signal, or in hot depth the signal penetrates through the analyte or material. So then go to for reflection monitor. For reflection monitor we will use here analysis group. From analysis from this group I will use the analysis, and from this analysis group I will set here the monitor, and I will use the frequency domain field and power monitor, that is here, and I will set this power DFT as I use this as reflection R monitor, and I need to set the geometry of R monitor. But before this I need to make the R, the reflection monitor, under this analysis group. So I will set this move into group, and now this under this group. So here from here I have to set the geometry of this analysis group. And here I will set this 0 0, and analysis script, this is variable, and here I will write a script that I will explain another thing, sweep. So I need to here transmission. Actually there is no direct function of like that mean direct function of reflection. So we need to declare it as transmission, then just we will minus it, and here that is the reflection is minus transmission R, and then another that I will get the field data from here. Okay, and another just I will set another field analysis group here. So just I will do the similar thing, analysis, and from this value I will set the oh sorry, I don't set the R value, so I need to set the R value, and from here the geometry will be not linear x, as I grown this along linear x, so I need to define it as linear y, that is linear y, and when I will linear y, that will be 0, and this can be minus 250 to 250 is enough. I will record this data, so it is okay. Just apply OK. From here, just say see here that the point is the data you can see here, the reflector monitor, that light will, if you can see here, like light will just hit the prism and metal interface, then light will reflect back this direction, and I have set this monitor which will actually collect the reflected light, and also from the reflected light we can see the reflected power. Then again at analysis group I will set at first the geometry of this analysis group, and that will actually record the field data. Just from here analysis group I will record field data, that I will make everything will be 0, because for here I use the value of metal axis at 0, so I will record the data from here, and it is 0, and I need to write the script file, that is like e2 e square power, that is e square equal get electric which will be field and x equal get data that will be field and just x. Okay, now I just need to add variables, the results will new results, that from here just say x and e2, so I need to set e2, then add x. Okay, I need to do same thing for analysis at script under this analysis. Here just from see the R and F, so I need to set the R, then add F. Okay, and analysis from here analysis group, simply I will set the name of this field I can set it as reflection and field. Also I need to set another frequency domain field and power monitor under this analysis group, and this can be renamed as also field, and this can be under move into groove, field groove. And I need to the geometry and other thing, like from here that will be field that will be at linear x, and from here I can use this just from minus 500 to 1500. Okay, then just in general, okay, data to record, I will record the data and just see from this structure, the reflection monitor, the time monitor, and also the other field monitor, that if I just disable this field, look, there is no yellow line. But if I enable this field, that field monitor is from minus 500 to 1500, and the field region will be calculated throughout this region. The field motor will record the data along this region. So I think almost we have done. So now look, for when you will read the paper research article, you will get a SPR curve like just as simple like this type of curve. When I will explain you that how can they achieve this curve, you can get this reflectance value from the reflectance monitor from one point, like at incident angle. When you will set the incident angle at 40 degree, say 40 degree, then you can get this point. When you set 41 degree, then this point, then 42, this 43, and it can be at 46, at 46 degree or 50 degree, you can get this point. But you cannot design this in this way. You need to set a variable parameter for angle sweep, that you need to define the angle can be vary from 40 to 60. So for this you need to follow here, just here, that is this point, this is sweep, and I will create a sweep and just click here and you will get this button sweep. And now just here from edit option I need to set this sweep. This is very crucial at this moment. This sweep, so I need to first design the source model, I have declared from this model the objects, that was source 1, and from source 1 I need to declare this angle theta. I'll set. Now this is number, and you can set it from 40 to 60. For example, you set it here 40 to 60. Just follow here, and this is the number of point. If you give 10 point, then it will give you the 10 point data of 40 to 60, but for 40 to 60, for difference of 1 degree angle, you need to set this at least 20 to 21 point. But for more accuracy, when you will use this point too high, then you will get the exact precision value for a small angle difference. Like resonance condition is very crucial here, so you need to find the exact angle where the resonance occurs. Like it can be at 46.5 degree, and for another analyte it can be different, like 48.9 degree. So it is very crucial if you calculate the value for 0.5 or 0.9, but you cannot make any differences if you don't make this number of points too high. Like 40 to 60, for 20 points you can run it for 300 or 400 number of points. It will take your time, but it will give you more precision. Okay, fine. That here you just set 20 points. Then from here, the results section, I will set see you from result section. Just add, like I'll set the R, select parameter model objects. Here actually I will record the reflection. So from reflection results is R. If you set the value of reflection R, then look model reflection R. Then again from here, that is if I want to record the electric field, that is model and objects and field data and results. That results will be electric field E2, and that's enough. I just want to record the reflectivity or E2, or you can also the X parameter value here. So model, go to here, model field results X, no problem. Just here you can see the operation, it will integrate all value 40 to 60 and it will give you result. But X is just position, so you need to set it here from as mean value. When you will set it this, then you set OK. That now your sweep has been set. Now, like just I said that the prism material here, but we can see the actual value of silver from refractive index info, like silver. I will use the value 633 nanometer. So when I said that, then the real part and the imaginary part value is different. And if we set this value for here, actually when I defined the material silver test, now I'm going to change the refractive index accurately. That will be here, and for this value I will copy that value from here and look at 633 nanometer. I am going to use this value. Okay, now also I need to change the material from here, silver test, like apply. Okay, but from here the color of material need to be changed, because this cannot be identified by using the analyte material and silver material for same color. Just I set that at red color. Okay, just check here, this is the prism material, long prism, then the silver material, that is red color, and my analyte material, that is this green color. Now I have set all sweep. Now if I ran this program. Before running this program, I need to save that. Just test. Just now I can run this from here. When I will give the run, it will take sweep 40 to 60. I don't know what will be the resonance angle. After calculating all, it will give us the resonance angle. I will skip this portion of this video for your time saving. Just I will see you the result. What will I get from here? Just wait for the result. But if your program is okay, if you set all the things in an organized way, then you will get everything will be good, and your all sweep option will be okay, and you will get the final value from here. Just look at here. That just one for a single run is not done, so I need to quit because I didn't declare any 2D material that has a smaller thickness. So I defined the silver material, and that was 50 nanometer thickness. So I am going to change this mesh, and you can see the result. I will set it for 5 nanometer. Like my silver is 50 nanometer, so this will not get a lot of impact. That I have set it 5 nanometer. Apply. Okay. Just I'm saving this, and from here just I will set it for 53 to 58, and that will be 5 point, and go okay. Run. It will calculate for just 5 point. I have set it just to check the program is okay or not. Just wait for minute. Look at here, every calculation has been done in very few seconds because I have increased the mesh length. So mesh length has a very important role to design SPR sensor for your accuracy when you will use the 2D material. Now let's check the result. I have designed the model. Just from here I will see the visualize, and my data R, E2 or X is here. From the I have shown you from a paper that the reflectance curve is like this, but here I will show you. Here see that I have defined a very small portion, that is 50 to 53 to 58, and you can see that the pattern is like that. So if you design a sensor by maintaining the right material parameters and everything is okay, then you can just set it, and also from visualize you can see the just electric field value, and this is the portion where the maximum electric field. So just here I have shown you the electric field or resonance angle that you will see a lot in different paper. So I'm just going to show you another thing, that when you will change the material, like 1.33 was water refractive index, but you need to design another material like refractive index that has 1.335, just you need to change it from here 1.335, then set it OK, then save the structure and run. Then you will get the different curve at different refractive index, and that's all, and that's the overall design. And finally I am going to show you just a output from my previous design. So just give me a minute. I am going to show you a design. Just sorry, the program is not loaded here. Okay, just see the output will be like this, or also from here I can see another curve like this type of is resonance curve you will get from this software, and from here you can calculate the sensitivity or FWHM or quality factor, detection accuracy, and a lot of things. So thank you all. If you have any question, comment below the video, and I will be very happy if I can help you. That's all.